SwayamPrabha. Digital India. Educated India.
So, a quick recap of what we discussed in the last class. So, we started discussing about modeling particle transport in prescribed carrier phase flows. So, in this case, we solved basically the single particle equations when the flow properties of the carrier phase are known. So, we started with the basic example of a particle injected into a uniform flow of air. So, the objective here is to find the distance and time that the particle would need to acquire 99% of the co-flow velocity, and we could derive that solving the transport equations. Then we considered the same problem, but when the particle is evaporating. So, in this case, additionally, we have to consider the mass conservation equation, or here we are using the d square law model. So, by solving the equations, we could get how velocity varies with particle size, and then how the distance would vary with particle size. And by integrating the equations from d is equal to d naught, that is the initial size, to 0 when the particle evaporates completely, we could find the distance traveled by the particle again. Okay. And in this case, we see that this basically depends on the vaporization time scale obtained from the d square law and the particle relaxation time, where both are defined based on the initial particle size. Okay. Next, the modeling of polydispersed droplets. So, in this case, we have to consider the behavior of particles of different size. One way to deal with this problem is to consider this characteristic size, or VMD, volume mean diameter, and if the mass injection rate of the liquid is given, then we can calculate the number of particles we inject per unit time. So, once we know this, then by assuming some theoretical size distribution, for example, Rosen-Ramler distribution, we can calculate how many particles of a given size we are injecting. And in that case, basically, we have to consider the transport equations for particles of different size. But before we get into this problem, I gave an example where we basically consider system of particles with same size. So, here, unlike the previous cases where we were injecting only one particle, here we are injecting set of particles, but all are of same size. So, here the problem is to predict the length of a liquid rocket propellant combustion chamber. So, how do we predict the length of the combustion chamber when the liquid injection rate is known? And also we make some suitable assumptions here. First one is that here we have a one-dimensional flow. We have monopropellant, that is, the chemical composition of the propellant is basically same. While in practical case, we may be using bipropellant, we may be having bipropellant systems also. But here in this case, the chemical composition of the propellant is fixed. Then, as I mentioned, we consider mono-sized droplets. All droplets are of same size. There is no droplet collision. So, the number of particles or number of droplets at any instant of time at any location basically remains same. And then importantly, we here consider that the temperature and pressure within the combustion chamber are constant. Basically, the gas density is constant. Then the gas composition also does not vary. And the droplets burn as soon as they enter the combustion chamber. So this is basically, and also we have droplet gasification under equilibrium vaporization conditions. So this is to ensure that the evaporation constant is basically constant. It does not vary. Though in reality, the evaporation constant would vary with the relative velocity between the particle and the gas flow. But here we are considering that that is a constant. Okay. So then if we go back to single droplet injection that we discussed previously, we get this as our length. What is this length? XF. This length refers to the distance where the particle would evaporate completely. So if I inject a particle, let's say instead of all these particles, if I have one particle and if I inject that, how long it will travel before it evaporates completely. And that distance is basically our length of the liquid propellant, the combustion chamber. Okay. So now, but in this case, we have only one droplet injected. And we get this expression. And if we assume that the evaporation time scale is much less than the particle relaxation time, that the droplets are evaporating or burning very fast. If we do that, then from here we get that the length is basically equal to the injection velocity times the vaporization time scale. So we know that this vaporization time scale, according to d square law again, is d naught square divided by the evaporation constant. So the point here is that the length here basically is proportional to square of initial size. So this means that it is very sensitive to the initial size and also the injection velocity. So now the question is, if we have multiple particles injected, how these results would change, and what difference now we will have compared to the single particle injection. So for this purpose, we can do a mass balance. This is only a simple mass balance that we are doing. So this is the velocity of the gas entering the system, and this is the initial droplet size. We have initial droplet velocity also. So this represents the mass flow rate of gas entering the system. This is the mass flow rate of droplets entering the system. This is mass of a single droplet, while this is the number flux multiplied with area, which is number of droplets injected per unit time multiplied with mass of each droplet. So this means total mass of all droplets. Now this mass, what we have shown on left side, must be constant according to mass conservation. And here we have again at any other location, this is the mass flow rate of the gas, and this is the mass flow rate of the liquid droplets. So from this we can show that the gas velocity should increase. Physically, this is because the droplets are burning. So the droplet mass is basically getting converted to the gaseous phase. So obviously the obviously the velocity of the gas flow should increase. So essentially that is the difference now with respect to what we did here. So in this case, okay, In this case, the carrier phase velocity was constant, but now it is not. So the gas flow is accelerating. So we have to account for that in the equations, and that is what we will do. And so here in this expression, if you put d is equal to 0, you get this. So this means that this term refers to the maximum gas velocity at the exit, where this term phi is the ratio of mass flow rate of liquid to mass flow rate of gas, which is known. So basically here what you are given is this UCO, that is the initial velocity of the gas, the mass loading ratio, okay, and the initial size and velocity of the droplets. So you have to now predict the length of the combustion chamber. So for this purpose, now again we consider the transport equations of a single particle again, but we have a system of particle. But should we consider all particles or just the equations for one particle? So even if we have all particles, the length will be determined by the condition that the particle size has to be 0 finally. So because all droplets are independent of each other, they behave exactly same way. So we can consider the single particle equation only. Okay. But now this UC is going to vary, and we have shown how it varies with particle size. So now I consider the momentum equation and the d square law and combine them to get this relation. So if we solve this, what will we get? We'll get how particle velocity vary with particle size, okay, and that is what we get. So here you have to integrate this. It can be theoretically done, but for this you need to introduce some suitable integrating factors, okay. But it can be solved analytically, this equation. So by solving this, you see that you get a big expression. So you get this big expression, but here the only variable is d, the particle size. Now here we have this parameter s, which appeared actually earlier also for the single particle equation. Basically this is the ratio of droplet vaporization time to droplet relaxation time, s, and V naught is the injection velocity of the droplets. So now if we consider two extreme cases, first case where this parameter s tends to infinity. So what does this mean? This means that the evaporation time scale is much larger compared to the relaxation time. This means that the particles would quickly adjust with the carrier phase flow, okay. So in this case, if you put s is equal to infinity in this equation, you get this expression, and you see that this is nothing but the velocity of the carrier phase itself. So this also physically makes sense. This means that if the particle relaxation time is much smaller compared to vaporization time scale, the particle is quickly adjusting with the airflow. So that is why the gas flow, its behavior is exactly same as the gas flow velocity in this limiting condition. The other case where s tends to 0. So this means that the vaporization time scale is much smaller compared to the particle relaxation time. So if you plug in S is equal to 0 here, you see that, okay, if you plug in S is equal to 0, here you see, you just get V is equal to V naught, which means that the initial velocity is just maintained. Okay. So now, but in reality, you have both of these parameters present, okay, which will influence the droplet velocity. So if we plot non-dimensional particle velocity, so this is just, I have normalized the particle velocity with this parameter. If you plot it, now you see that for S is equal to 0, see V remains constant. This is equal to V naught. But here I am showing the non-dimensional particle velocity with particle size. Here we don't get any information about the length. Here we are only seeing how velocity varies with particle size, that's all. So now you see this case where S tends to infinity, the plot is like this. So first the particle velocity reduces and it becomes equal to the velocity of the carrier phase, and then the behavior is just exactly similar to the way the gas flow velocity increases. However, for intermediate value of S, you see the trend is like this, which means that initially the particle velocity decreases and then it increases. Okay. So now we can consider, so the next objective is to find out the length. So for this purpose, we have to solve these two equations as we did earlier. So again here you will have to plug in the value of the V that we have obtained here and then solve this. Integrate particle size from initial value to 0. So if you do this, you get this expression again. Okay. So now this tells us which parameters influence the particle, the length of the combustion chamber. So this is basically the minimum length of the combustion chamber which you must have to ensure that all droplets burn. What is the problem if it is not, if the length, if actual length is less than this, then what is the problem? You are basically losing the energy. So the combustion efficiency is basically low. Okay. So now in this case also, if we put the same limiting conditions, we get this expression, and if we compare with single droplet injection, we see that they are close. Especially in this case, you see that the expression is just same in this limiting condition. Now, what are the influencing parameters? So from this expression, we understand that the length of the combustion chamber, or the minimum length of the combustion chamber, basically depends on the initial gas velocity and fuel to oxidizer ratio, the mass loading ratio. However, these parameters are specified always. This is depending on the rocket performance that you want. These parameters are specified. You can't play with this. Okay, but then what are the controlling parameters? Controlling parameters are these two. That is the initial injection velocity and initial particle size. So how do we minimize the combustion chamber length? By reducing the droplet velocity. But also we get some quantitative information. It is not only we get this information in a qualitative sense. No, so you look at this parameter. So this is basically initial injection droplet velocity divided by, what is this? This is the exit velocity. We we derived this expression just before. So this represents the ratio of the droplet velocity at the entry to exit velocity at the exit of the combustion chamber. So this means that you have to make sure that this ratio is low. Now, on the other hand, depending on the type of injector we use, this V0 may have to be increased. For example, if you use pressure-based injector, if you select a pressure-based injector, which means that you pressurize the liquid to high pressure and then inject it. Higher the pressure, better is the atomization. But higher the pressure, V0 is also high. So then there is a trade-off. So if you go on increasing the V0 to get small size, the length may increase even if size reduces. Okay. Another important point here is that independent of what other parameters appear here, the length is again proportional to d naught square, which actually we get from single particle equation also in uniform carrier flow condition. So this means that if you reduce the particle size by 2 times, the length of the combustion chamber may reduce by 4 times. So this means that it is very sensitive to the particle size, and so good quality atomization is very important. So you see how the main objective here is to demonstrate how we considered a practical problem, and then by making suitable assumptions, we solve the equations, and finally we get the expression which tells us the main parameters which control the length and also the sensitivity of those parameters. Okay. Okay. Now we will consider another interesting example. This is the same example that we did earlier. However, till now we have been considering only one-dimensional flow of particles. Okay. Can we handle if we have more than one dimension? So we are revisiting the same problem, that is, we inject one particle into uniform flow of air, but now gravity is important. Okay. So the objective here is to find the droplet trajectory and suspension time of the particle in air. So how do we approach this? So again, like the previous case, here we have to solve the momentum equation and the mass conservation equation or the d square law. However, now we have both components present. Okay. So if you see here, I have written this for the x component. Okay. So this part is exactly same as what we did earlier. Okay. However, solving only x momentum equation is not enough. Why? Because the droplet may reach the ground before complete evaporation, because it is being transported in the direction same as the gravitational direction. So momentum equation in y direction must be considered. So now let's see the momentum equation in the y direction. So here what difference you observe? The y I have put here 0. No, this one. Here you have u minus v. This is actually uy. So in our case, we have a uniform flow. So y component of the gas velocity or air velocity is 0. And here we have y component of the droplet velocity. But now in addition to the drag term, we have the gravitational term. Gravitational acceleration also has to be considered. And here we have chosen the coordinate system such that the direction of y aligns with the gravitational direction. Otherwise, it's not like this is compulsory. You can also choose y in the upward direction, but accordingly you have to account for that. But this simplifies the analysis. Now, the remaining equations are same. So, again we have to repeat the same process. Now, here we can combine this and we can get expression for y component of droplet velocity in terms of particle size now. So, this is also analytically solvable, though again this requires introduction of some suitable integrating factor to facilitate the integration. And then by combining these two equations, we can get the expression for y also. So, you have now expression for Vx, x, Vy, y all in terms of particle size. So, you can write a parametric equation representing the trajectory of the droplet. So, you know x is a function of particle size, y is a function of particle size, and then for different particle size as it evaporates, you can calculate the coordinate of the droplet and you can see what is the trajectory of the droplet. Then we need to calculate the vertical distance travelled by the droplet before complete evaporation. So, you need to calculate basically the final y. However, here we have to compare this with the height at which the droplet was injected. So, that height must be known. So, if this height is larger than the final distance, this means that the droplet would evaporate in the air only. So, or before reaching the ground. So, you can find the corresponding value of the axial distance. So, this axial distance tells you how far the droplet has gone by that time. And then you can use this equation or d square law to calculate how long the particle stayed in air. So, that is the particle suspension time. On the other hand, if the yf or the final distance is more than h, this means that the particle has fallen on ground. Okay. So, in that case, it will evaporate there itself, and that limits the axial distance that it can travel. Okay. So, now you see that you can now change the initial particle size and see the behavior for particles of different size analytically. So, intuitively it will happen that if the particle size is very small, then it will evaporate before it reaches the ground, but if it is large, then it will fall. Okay. But you can quantitatively evaluate this effect. However, a very interesting phenomena occurs here. See here, basically if you look at this equation, okay, and try to see what would happen if the particle does not evaporate. What will happen? What will happen to this velocity? Let's say you inject a solid particle. What will be this velocity? What would be this velocity? Finally, we had discussed this in the previous class. This will be equal to the terminal velocity of the particle, right? Now, do you get that expression? So, if we assume that d by d naught is close to 1, then it is possible to show that, and also this term, the vaporization time. So, if a particle evaporates very slowly, then what would happen? This is much larger than this, right? So, if we put this, then we can show that this is essentially equal to, in that case, particle relaxation time times the acceleration due to gravity. This is nothing but the terminal velocity for a non-evaporating particle or a particle which evaporates very slowly. But now imagine what would happen if the particle evaporates. So now if you look at this equation, okay, now what would happen to the right hand side when the particle is just released? You have just injected. Right side, if you see, because your initial velocity in y direction for the particle is 0. You are injecting the particle in x direction only. Okay. Now, in that case, this term is 0 at the initial time. Then what you have here is only gravitational effect. So, that is why this will accelerate. So, in the next time, you will have some finite value of Vy. And how long this will go on? This will go on till this term is equal to this. Then you reach terminal velocity. But what can happen is that this term may be higher than this, because your particle size is reducing also. So, this term is reducing. This is not a constant. Tau d is not a constant. Okay. So, what will happen actually? Are you getting it? So, the trend will be something similar to this. So, right after injection, the particle vertical component of velocity of the particle would increase, and some terminal velocity will be reached. But once the terminal velocity is reached, then what happens? So, then the particle velocity cannot change, right? But the particle size itself is changing. Are you getting it? So, then here if we assume that the momentum response time or the particle relaxation time is very small and it quickly adjusts, then what will happen is that the terminal velocity is always retained, but the terminal velocity itself reduces with particle size, because your particle size itself reduces. So, the terminal velocity will also reduce. Terminal velocity is not a constant because particle size is not a constant. Okay. So, when you solve this, especially numerically, you may encounter this situation. So, at that time you have to implement such model. Okay. Okay. So, so now we know how to account for multidimensionality. So, even if we have, let us say, 3-dimensional transport of particles, that also you can do it. Okay. Now, as of now, we solved the single particle transport equations under some assumptions. That is, we always assume that Stokes' drag law is valid. There is no convective effect on particle mass transfer rate. All these assumptions were inherently present. Okay. That is why you could theoretically solve the equations. But if we account for that, for example here, so this is the d square law. So earlier we considered this term as 1. So which means pure diffusion. So square root number, if you put Reynolds number is equal to 0, square root number 2, so here you don't have any effect. So we assume that the Reynolds number is 0, but the Reynolds number is not 0, because always you have some finite relative velocity between the particle and the flow. Similarly, in this case also, in the momentum equation also, you have this nonlinear term present where, okay, this RER means this is relative, based on relative velocity. Okay, and this is also according to one model. Okay, if you change the model, this expression may vary. But the question is, how do we solve these equations now? It is no more analytically solvable. So we can solve it numerically. Okay, so for that purpose, we can discretize the transport equations. And for simplicity, we can assume explicit finite difference method. So like this, for example, if you have the momentum equation, you can express this using finite difference method. Okay, so you can consider, let's say, forward scheme. So the rate of change of velocity divided by this time step delta t, this is equal to whatever term here you have, that is evaluated at time t. So the only unknown here is t plus velocity at t plus delta t. So it is possible to write a simple, let's say, MATLAB or Excel code to evaluate this. But here you have to make sure that you calculate Reynolds number at every time step, because the slip velocity is changing, the particle size is also changing. Similarly, the particle relaxation time also changes. So you need to update this at every time step. But once you calculate this, just plug in all these here, okay, and go on evaluating the velocity. And once you know velocity, similar way you can calculate the variation in the spatial location. Okay, same way you can calculate this. So basically here the right side is considered as a function of the previous time step. So that is why it's called explicit scheme. So similarly, we can discretize mass transfer equation or energy transfer equation. Okay, but the most important point here is the choice of the time step. How would you select what is the time step size? So for example, in case of momentum equation, your time steps should be much smaller than the particle relaxation time. Okay, then only you will be able to solve it properly, or you will get accurate result. Okay, so this has to be kept in mind. However, if you are solving both energy as well as mass transfer equation, you have to ensure that this time scale or this delta t is smaller than the droplet vaporization time scale also. So you need to consider the characteristic time scale of each process and make sure that the delta t or the step size is smaller than all three of them. But usually the momentum response time is smaller than the vaporization time. However, it depends on the application. You should not always assume, rather make an estimate and then decide delta t. For example, if I ask you, okay, now do the same problem, solve the same problem numerically, a 100 micron particle is injected into a stagnant ambient condition, find its trajectory. Then you can do that by solving the transport equation and accounting for all this. But for that purpose, first you need to calculate the particle relaxation time, okay, and the vaporization time based on the initial size, and then decide what is delta t. Okay. So after this, I will show a an example which is close to reality and which is more involved. So here we need to model respiratory droplets. So imagine someone is coughing or sneezing. A person is standing and coughing. So how far the droplet cloud would be transported? What will be the distance from the injection point? How long the droplets would suspend in air? These information are very essential if we want to restrict infection. Okay, kind of a scenario that we recently experienced. Okay, but here we are going one step ahead of that, and what we want to do is that we want to make prediction of this droplet cloud transport under group evaporation effect. What is that? I will discuss soon. So here, as I said, what is the problem definition? Here we have to predict the trajectory of a droplet cloud ejected during human coughing process. We have chosen coughing process because the sneezing process is more complex, because that involves atomization of the saliva even outside the mouth. So we don't want those complexity. Then estimate the distance traveled by the droplet cloud and suspension time in the air. Study the effect of co-flow. So if there is a air flow around a human being, then how these parameters would be affected. Now let's say there is an air flow around you at 1 meter per second. So now how much increase in the distance you expect because of that, and how much increase in the suspension time you expect. Similarly, what is the role of ambient temperature, relative humidity, okay, how they affect these parameters. And finally, as I said, influence of group evaporation phenomena on the predicted results. So these are the objective here. So if you see, here we have extended the previous example. In the previous example, we had only one droplet. Here we have a group of droplets. Okay, so just to give you a basic idea of what is group evaporation effect. So till now we have been considering basically the isolated droplet evaporation model. So D square law is basically a model which refers to isolated droplet evaporation. So in this case, each droplet vaporizes in an isolated manner. So as I have shown here. So you imagine this cloud of droplet has come out, but each droplet is evaporating individually, and there is no mutual interaction of the released vapor around neighboring droplets. So there is no interaction between the vapors released by the nearby droplets. However, group evaporation refers to a scenario where the cloud itself evaporates collectively. This entire cloud evaporates instead of individual droplet evaporation. And in this case, the droplet evaporation rate can be much lower. So what is the issue if the droplet evaporation rate is lower? If the evaporation rate is lower, then obviously the distance traveled by the particles would be higher. Okay, and their suspension time also may be higher. That's what we will have to check that. And this is characterized by a number called group number. And interestingly, this group number came from a group of researchers who worked in combustion of fuel droplets. So what they argued is that in a combustion chamber, rarely a droplet would burn with a flame around it. No, that's not usually possible. When we inject the droplets in the form of a spray, most of the droplets burn as a cloud, one cloud. Okay, that's what their argument. So they developed a theoretical model, not by considering a practical injector, but by considering a cloud of droplets, okay, a cloud of, an isolated cloud of droplets. So earlier we had only one droplet. Now you imagine there is a cloud of droplet, but that is isolated from any other cloud. And then they developed a theory and they came up with a number called group number. As you can see here, it depends basically on the number of particles that you have in a cloud and the interseparation distance between them. And they came up with this number called G. So if the value of G is much less than 1, then you have isolated droplet evaporation. However, if it is of the order of 1 or more than 1, you have this group effect prominent. So if we can calculate this G number, it will tell us how significant is the group evaporation effect. Okay.